the concept of continuity for real valued functions. And we did some proofs using a formal definition of continuity, the epsilon delta definition of continuity. And now we're coming on to finally introducing the definition of the derivative. So we're beginning the study of integration with Said and the other stream of this unit. And so very much hand in hand with that goes the concept of the derivative. And we'll be interested in doing, two sorts of things with this material. We'll be interested in looking at, kind of applications of it to other areas of mathematics and uses that you can put this concept to. And also building up a bit of a body of theory about the derivative as well, and giving rigorous proofs of properties that the derivative has in order to justify all the work that we do. Now, of course, in your earlier study in mathematics, you will have had exposure to the notion of the derivative before, but we just go back over the definition of it for you now. So this is the derivative of a function. Now let's say just a function from the real numbers to the real numbers, or equally well you can apply this to functions from, maybe not defined on all of the real numbers, but a subset of the real numbers. But these are definitely real valued functions taking values in the real numbers, and the arguments are real numbers as well. So, here's our typical wavy graph of the function. And the derivative is this concept that captures the notion of how the function is changing at a particular point. Okay. So we might choose a particular point A in the domain of the function. You can see here the value of the function f of A. And the derivative is some way of capturing the notion of how the function is changing at that point. Is the function increasing as you go through A, as you move past A from left to right, from smaller values to larger values of A? Is the function increasing? Is it decreasing? And more than that, how fast is it changing? How fast is it increasing, or how fast is it decreasing? Okay. So the derivative captures the concept of how the function is changing at A. A little bit vague for the moment, at A. So in order to lead us into the definition, we might think about, well, one way you might do this is to say choose your base point A, choose another point which we'll label as X, and compare the two values. You've got an f of A here. I didn't draw it that figure, maybe the f of X is slightly higher. So the very first thing you might do is just compare the two values. Compare the value of the function at A and compare that with its value at some nearby point X. And you might observe one being greater than the other, and you might take note of how large that difference is. But that shouldn't just be viewed on its own, because the function might only be slowly changing, but maybe your X is very far away from the base point A. So even though you observe a large difference here, if the value of X you chose was very far away from A, then that large difference here could still come from a function that's very slowly changing. Or, on the other hand, if you just observe a very small difference here, you might think, okay, the function isn't changing very much, but then maybe the X you chose was extremely close to A. And even though the function only changed a little bit, if it only changed that little bit in a tiny movement away from A, then the function could really be very fastly changing, changing at a very high rate at A. If you've only moved x a little bit, you've only given it a chance to, even though it's really changing a lot, you've only given it a chance to change a little bit. So this difference, the difference between these two quantities shouldn't be viewed on its own. It really should be viewed in comparison to, or relative to, the amount of change you've introduced in the domain of the function. Okay. So we might assess the behavior of f. The behavior of f by examining the difference f of x minus a, f of x minus f of a, the difference in value that the function has between 2 points. But as I said, you know, whether this is big or large and how much significance we attach to that really should be viewed in comparison to how much you changed away from the base point A. The function could be very slowly changing, and you could have gone, you know, millions of miles away from A, so to speak, and then observed a huge difference here, but really the function is really only changing very slowly. On the other hand, you might have only stepped a tiny amount away from A, a really insignificant amount of distance away from A. You might have observed a small difference here, but nevertheless, the function could really be increasing very fast. You've only given it a chance to expose a very tiny difference. So we might assess the behavior of f by examining this difference here, but to really assess this difference and what it means, you should view it relative. To the change you made in the domain. Relative to the change you made in the domain, you can capture that by looking at the difference between x and a. Difference x minus a. And well, if you've got two quantities and you want to examine one relative to another, the natural way, meaningful way to do that is to form a fraction, form a ratio. Okay. So we can examine the ratio f of x minus f of a compared with x minus a. So you move x a little bit, and x minus a, this quantity here, this will capture which side of a you've gone. So if you go to the left of a, if you go to a number smaller than a, this difference here, x minus a, will be negative. Because if you go to the right of a, to a number bigger than a, this difference x minus a will be positive. So that is captured in this, and then equally well, if f of x minus f of a is positive, it means that the function is increased a little bit when it's moved to x, and if that function is negative, it means the function is decreased a little. So being able to examine the sign of this, the sign of the ratio, you can figure out whether the function has genuinely increasing as you move from left to right, or decreasing between those 2 points a and x. Now this ratio actually has a very strong geometric meaning to the graph here. And if we consider, what we do is we consider the straight line, the chord drawn through, mine be exactly straight, but I just wanted it to intersect the x-axis within the picture. So you see, you got a straight line here, okay, moving through these 2 points, the points in the graph of f at a and x. And you get a very natural angle associated with this line. So this, the angle that this makes with the horizontal. Of course, that line is also present here. Imagine draw another horizontal line parallel to the x-axis. This angle theta it's not the greatest picture in the world. That angle beta is the same as that angle up there, because it's the same diagonal green line. That's really one straight line. Anyway, it's that same diagonal straight line, and this vertical, or this horizontal bottom of this triangle here is parallel to the x-axis. So these two angles are the same. So actually, and this f of x minus f of a, that's this vertical distance up here, and x minus a is the length of this side down here, and you form the ratio of those, and that has a well understood, a well understood quantity. That's the tangent of this angle. Okay? So in fact, tangent of this angle is equal to f of x minus f of a over x minus a. This is called the gradient. Called the gradient of the chord or line through these 2 points. So one point is a, f of a, and the other point is x, f of x. So you've got your straight line. Part of the straight line is very shallow. Function isn't changing very much. The straight line is very steep. Function's changing a lot. But so how is this doing at capturing the behavior of the function? Well, okay, it captures the behavior of the function when viewed at the point A and at the point X. But what it doesn't capture is what the function is doing in between A and X. Okay? So of course, the function f might be doing other things between this a and x and still have the same gradient. The gradient as measured in this sense, because I mean here's a graph of a function. Here's another point A, another point X. Okay, the function is changing in a certain way between A and X, but the function doesn't have to be doing this. You can still have a perfectly good, well-behaved, continuous function, which does other things between A and X. But this definition of the gradient doesn't see what the function is doing here. It only just captures its value at A and its value at X, and it forms a ratio. The ratio of those changes, and that is the gradient of the straight line drawn between these two. Function might be, the function might suddenly increase extremely fast and decrease extremely fast. It might have all sorts of weird behavior between A and X, but this definition of a gradient, is oblivious to what the function is doing between. Okay? So this definition of the gradient captures how the function is changing from the point A to the point X. But we want to get this idea of more capturing the essential change, the essential nature of the function right at the point A. So to do this, this is why I'm explaining like this, it kind of motivates the definition that we should look at this value of the gradient, but we should examine it as we let x get closer and closer to a. Because as you let x get closer and closer to a, you've always got this definition of the gradient, how the function is behaving between at a and compared with at a and at x. But the value of x you're using is getting closer and closer to the point A itself. So you're getting closer and closer to that idea of capturing the behavior of the function at the point A. Not at the point A and at another point X slightly away from A, but essentially at what it's doing at A as well. So to capture, to get to the behavior of f at A, not at A compared to another point X, but just what it's doing at A itself, that kind of motivates us motivates us towards the definition of the derivative. Towards the definition. Okay. And we have, we have in our arsenal of stuff, ideas we can talk about, we have this idea of the limiting value of the function. Okay. So we simply take the limiting value of the gradient. Okay. So this is in the notes, this is definition 4.3. You look at the gradient, which measures the change in behavior of the function compared with the value it's taking at A and the value it's taking at X. But you look at how this quantity behaves as you let X approach A. Take the limiting value of this as X approaches A. Okay. So this is the derivative. This is the derivative of F at A. This is what it's named. Just pick out a bit of a discussion in the notes there, but I'll just pick out important bit. I mean, there's two main types of notation used for it. Traditional notation you're used to is this df dx. That denotes this other function, which is the derivative of f. It's actually, if you apply this definition to any point A at all, what you get is actually a function of A. You actually get a function of the variable. So this particular limit here, you can often denote that as saying it's the derivative of f, and we just have a straight line as a border to this object and then a subscript x. So that denotes the derivative of f at that particular point A in its domain. Or slightly more compact notion is just to use this superscript of a dash. It's not quite, well, in some senses it's a 1, but just a dash on the function. Superscript dash indicates the derivative of the function f, and evaluated at A means we're talking about the base point A. One of the advantages of this notation, df dx, is it's more natural to see it as an operator ddx applied to f. So it kind of suggests the existence, this we can write as ddx applied to f. So it kind of gives identity to the operation of differentiation itself. It's a thing in itself. It's an operator which can apply to functions. Whereas in this notation, the thing itself, the act of differentiation, the operator is just signified by this little line, superscript line. You can't really talk about a superscript on its own without a letter to superscript against. So that's one advantage of that notation here. But this notation is maybe a little bit cleaner, a little bit simpler in a typographical sense on the line. It doesn't change the height. I mean, this thing is normally a fraction, so it's normally taller than the surrounding letters, whereas this thing just after the dashes fits in better with the sentence that you're writing. So, okay, and we should go back to our geographical picture. So we had these chord lines which were in green. Okay, green doesn't come into it, but just looks black as well. And so here's the base point A. As x gets closer and closer, these are different values of x. As x gets closer and closer to A, these chord lines are changing, of course. But as x gets closer and closer to A, these lines eventually they'll start to not change all that much. Okay? They'll start to settle down in their behavior until you get to a kind of a limiting one down there in red. So this limiting line of the chords as x approaches a, this is a special name, this is called a tangent. Tangent to the graph of f at a. So that's our definition of the derivative. I've tried to kind of indicate two aspects of thinking about it. There's a very strong geometric way of thinking about it in terms of how you attach it to the geometry of the graph of the function. In terms of these chords going through different points in the graph. There's a triangle there with that chord as a hypotenuse. So the way you capture the behavior of that chord is to talk about its gradient. The gradient is the ratio of those differences, f of x minus f of a over x minus a. You also think of it as the tangent of the angle, theta, in the bottom of that triangle. This angle over here is a right angle. So there's a very strong geometric way of thinking about it, but then there's also this very nice way that you can kind of arrive at the definition without talking explicitly about triangles or anything, but just talking about assessing the difference between the value at one fixed point A and the value that it takes at a nearby point. And the recognition that you oughtn't to just look at the difference on its own, but just looking at the difference on its own doesn't tell you that much about how f is behaving. You really need to know how far away x is from the point A. Then you judge the size of this difference relative to how far x has moved away from the distance. So you should view this f of x minus a relative to x minus a. And what that means is you look at the ratio of the two. Okay? Because this ratio will be large when the numerator is large compared to the denominator, and the ratio is small when the numerator is small in comparison to the denominator. Even when you just look at tiny movements in x away from a, so you're going to see tiny differences here and probably tiny differences there, but yet the ratio might still be a very large number or a very small number, depending on how those differences compare. Okay, now before we get on to an example or two, just a few words about, well, okay, this all looks great, that definition, there's no problem with it, except we've defined it as a limiting value of something. And from our experience with limiting values, looking at sequences, series, limiting values of functions, limiting values don't necessarily exist. Okay? They exist when the thing you're taking the limit of behaves kind of nicely in some sense, but they don't always exist. Okay? So we should just say a word or two about that. Okay, so of course this limit might not exist. If it does, if this limit up here is if it exists, if there's some real number that is the limit of that quantity. If it does, the function f is called differentiable at a. It has a derivative. But not all functions are. Differentiable at every point in their domain. For instance, it's a requirement that the function be, at least it has to be continuous. Okay? So if the function is not continuous at a, it won't be differentiable. And you can see that easily enough. I mean, if, well, we draw one example of a function that is not continuous at A. So this function is making an instantaneous jump in value at the point A. Well, this causes a problem because if you compare, let's say the value it takes at A is down here. If you compare a nearby point X up here, these X's, and you look what happens, oops, what's happening to the chords. Chords, when you look at those points, as X approaches A here, the chords are getting steeper and steeper. And the limiting chord, in a sense, is going to be vertical. But what's the gradient of these? See, as the chord gets steeper and steeper, it's got unbounded gradient. The gradient is just getting larger and larger. There's no upper bound. So in a sense, the limiting value of the gradient of the chord is infinity, which we don't admit is a real number. So we'd say the limit of the gradients of these chords, it doesn't exist. There is no limiting value. And that's just if you look at points to the right. If you look at points to the left of A, you know, compare A to the behavior at these points. Well, there you've got a much more reasonable behavior. I'm using a different color. The different colors don't seem to come out. You know, here the chord lines are showing much more reasonable behavior. They are settling down to, this one is kind of almost nearly the tangent line, but you know, so there's going to be a tangent line which is quite similar to this line I drew going through this point, which is closest to A there. So we have what looks like reasonable behavior to the left of A, but unreasonable behavior to the right. So simply according to our definition, the limiting value here, the limit as X approaches A of this f of X minus f of A over X minus A does not exist. You can, okay, widen out or make the definition a bit more detailed and say, well, it does have a limit when you approach it from the left, but it doesn't have a limit as you approach it from the right. And you can talk about left and right-handed derivatives of functions as you approach it from either way. But according to our definition, there's a problem here. This function would not be called differentiable at A. It doesn't have a well-defined behavior at the point A that can be captured in this single number, which measures its rate of change. The situation is more complicated. But it isn't just, so it cannot be differentiable because it's not continuous, but just because it's continuous does not mean it's differentiable. Okay? So you can still have problems if the function is differentiable, is continuous. Just being continuous doesn't guarantee that you're differentiable. And not a specific example, but just a kind of a little bit of a sketch. So here this function looks perfectly great here. So, okay, it's nicely, smoothly changing most parts of its domain. There seems to be a problem here, at this point here. So this is our A that we're talking about. What's the problem here is that this A is like a sharp point on the graph. It's still continuous. There's no break in there's no break in the behavior of the values of the function at this point. That the graph isn't split apart at that point. But it is like a sharp point. Put your finger on it. Okay, it's a sharp point. And again, if you look at nearby points to the right, how would these chords be behaving as you let X tend to A from the right? I won't draw loads of them in my picture, but they'd be getting steeper and steeper like this. So these gradients are all negative. So if the gradient is decreasing from left to right, you have a negative gradient. As the point gets closer and closer, they're getting steeper and steeper like this. So they're going through higher and higher in absolute value, negative values. Okay. Whereas if x approaches a from the left, you're going to have chords like this. Now, these are increasing chords as you move from right to left, so they've got positive gradients. And they're getting steeper and steeper, so they've got higher and higher unbounded positive gradients. So the behavior of that gradient ratio, f of x minus f of a over x minus a, it's tending to minus infinity as you approach a from the left, and it's tending to plus infinity as you approach a on the right. So very different behavior on the left and right. Okay. So here, the limiting value as x approaches this a of f of x minus f of a over x minus a does not exist. Unbounded, it's unbounded with opposite sign on the left versus the right. So as you approach a from the left, you've got unbounded positive gradients. As you approach a from the right, you've got unbounded negative gradients. And the problem here is caused by this point here, this point A here, this sharp point. And indeed, so not the word sharp, but the word smooth. So you can say the function is not smooth at A. It's sharp, but the reason I use smooth instead is not smooth at A. Smooth is actually a technical term. When you look at, if you look at differential geometry, pick up any book on differential geometry or differential topology, these kind of more abstract subjects, which are generalizations of the calculus. The word smooth appears all over, smooth and non-smooth. Smooth is a technical term. And it essentially means if a function is smooth, it has a derivative. And if it's not smooth, like here, this sharp looking point, it's not smooth, there, it's sharp, then that's because the derivative does not exist. So that's our definition. And kind of tried to give a lot of motivation for it there. Why it is the way it is, rather than just kind of dropping it out of the sky onto the page. Tried to explain how we arrive at that, why that's a reasonable thing to look at, that limiting value, and link it quite strongly to some geometrical things associated to the graph. But we might also want to just get a bit more practical and start doing some calculations with this definition. So what we're going to do is we're going to look at some simple functions and see if we can apply this definition to work out the derivative of these functions. Okay, so working with the definition, so we'll look at one example. We'll consider this function. Consider the function f of x equals, say, k times x. K is some real number. So we're looking just at the function that is just some multiple of its argument. Okay? And a pretty simple enough function. Drew its graph. Drew the graph of this function is just a straight line. Okay? It's a straight line with with gradient k. Y equals mx plus c, it's going through the origin. K is the coefficient on x, so k we understand is the gradient. So we should find, if the derivative is the same as the gradient of the function, we should find that the derivative of this is k. That's what we should find. But we'll use the definition. So for any a in the real numbers, if we try and look at the derivative of this function f at a, well, by definition, so I just write down the definition, I just repeat the definition, that's the definition. Okay, but I know what f is. I know exactly what f is. F is k times x. So I've got k times x there minus k times a over x minus a. You see here an example of how the derivative, it's measuring the behavior of the function at a, but it doesn't actually depend, the derivative doesn't actually refer to the value of the function at a itself. I mean, you can't just figure out this limiting value by just substituting x equals a into it. If you substitute x equals a, then you'll have a 0 on the top and a 0 on the bottom. And there's nowhere you can go with that. You just have 0 over 0. That doesn't define anything. So you do genuinely have to look at the limiting value that this ratio has as x approaches a. Not the value, and that isn't captured necessarily by the value that it takes on at x, simply into the formula. What you have to notice here is, well, actually you've got a factor of x minus a on the top and the bottom here. So you've got a k times x minus a over x minus a. So you've got the same quantity as a factor on the top and bottom of a fraction, so they can be cancelled with each other. And you're looking at the limiting value as x approaches a. So in this process, x is never actually equal to a. It's just getting closer and closer to a. It never bumps into a. It never passes through the value a. It's just getting closer and closer. So there's no problem about dividing by 0. These quantities x minus a, they're never 0. They're getting extremely small because x is getting close to a, but they're never actually 0. So we can always, we're justified in cancelling it, dividing by x minus a, top and bottom of this fraction. Because we're never dividing by 0, because we're just looking at the limiting behavior as x approaches a. So those can just be, strike out those common factors from a fraction, and you're just left with the limiting value as x approaches a. K is just this constant that features in the definition of the function. The limiting value as x approaches a, well, there's no longer any x here, so this is always just stuck at the constant value k. So this limiting value is k. So that's nice. That agrees with our definition. That agrees with our intuition about, because this function, because its graph is a straight line, tangent lines to a straight line will always be the same line themselves. And so the gradient, the derivative, does always come out as being equal to k. That's our first definition. First example. We might look at another example. Yeah, that's squared example. So second example, if you consider g of x to be x squared, say. This can be done in a similar way. Oh yeah, so sorry, just before I leave the previous one. The example showed that the derivative of f at a was equal to k. So we can then speak of we can say that the derivative of f now is a whole new function. It just always takes the value k. It's always fixed at that value k. Because that works for any a in its domain. So we now have a function defined on the whole of the domains. We can do a similar thing here. Okay, talking about a function g now, so it will be the limit of g of x minus g of a over x minus a. A bit more quickly. So g of x, we understand, is exactly x squared. G of a is exactly a squared. And you've got x minus a at the bottom. Again, you can't just simply substitute x equals a here because you're looking at a fraction, and the top will be 0 and the bottom will be 0. So Can't just do that. But we do notice that, again, just like before, we can cancel x minus a. There's a difference of squares. You should almost have your vision trained that every time you see a difference of squares, you imagine x minus a times x plus a over x minus a. So again, once again, x minus a is a common factor. So what we're just looking at is the limit as x approaches a of x plus a. Now this, you can just substitute in the limiting value a of the argument x. There's no problems here of anything 0 over 0. You're just saying, how does this come to the x plus a? How does it behave in a limiting sense as x gets closer and closer to a? Well, that's going to get closer and closer to 2 times a. And this was for any a in R. There's no special restrictions on the value of a. So the derivative of this function g at a, it's always 2 times a. So that allows us to say we have a new function. G of x is equal to 2 times x. The derivative of this g is equal to 2 times x. Just as you look at other examples, okay, we've done x squared. As you look at higher and higher polynomial terms, you can deal with higher order terms x to the n using, this should be kind of part of, you should be seeing these kind of things in your sleep really, math students. Whenever you see a difference of the same integer power of a thing, so x to the n minus a to the n, that always factorizes as well. It might factorize a lot depending on what n is, but at least you can always extract out the factor x minus a out of that. And what's left behind, you can write compactly, it's the sum of products x times a, and you've got a j there, and then you've got a n minus 1 minus j there. The j goes to 0 to n minus 1. So you can always extract the factor x minus a out of that, and what gets left behind is a polynomial in x and a, mixed order terms. So that would look like x to the n minus 1. When j is 0, well, I'm writing it backwards now actually. When j is n minus 1, you get x to the n minus 1. When j is n minus 2, you've got x to the n minus 2a. You've got x to the n minus 3 a squared. The total index on these terms, when you add the indices on x and a, the total index is always n minus 1. So that would go all the way to x a to the n minus 2, and then the very last term is n minus 1. Sorry, that's written out backwards to how you would naturally write this out. So the j equals 0 terms up here, j equals 1, j equals 2, etc. J equals n minus 1. So you always have at least that factorization. Depending on what n is, you may get more extra factors coming out of that as well. Okay, that's just kind of an aside. For future things. Okay, so I'll see you again with this tomorrow afternoon, and we'll start to look at some properties of the derivative and some more examples. Okay, listening?